Hey there everyone, welcome back. I wanted to make a quick video describing two of the primary examples of our Archimedes principle, namely why ships float and why they remain stable. All right. So on the left, we see two shapes of iron, right? Two configurations of the same mass of iron. So iron is very massive, it's very dense, and so it weighs a lot, right? It's really heavy. However, on the left here, we see an iron cube, okay? On the right, we see that same mass of iron, but, stretched and contorted such that it's in that U shape or that bowl shape. Um, on the left, for the cube, the volume of water displaced, right here, the weight of that volume of water is less than what the cube actually weighs itself. Okay, and you can kind of see that in the length of the vectors, right? Right here up top, that arrow is the buoyant force, right? Buoyant force, remember, is, let's write it up here. Buoyant force equals the density of the fluid times g times the volume of fluid displaced. And so the volume is just, the volume of that cube, length times width times height, and the density of water is whatever it is. So the buoyant force has this magnitude. It's relatively small versus the weight of that water. And that comes from, rather, the magnitude of the buoyant force comes from the volume of fluid displaced. So if you can somehow increase that volume, well, if it's the same mass of iron, in this case as in this case, its weight remains the same. It doesn't change. But it depends on how you configure that chunk of iron, right? That mass. So over on the right, if you can displace much more of that water, right? This entire volume is much greater than this was, even though the picture may not look like it, right? You can picture this boat here as being very long into and out of the page. Okay, so this volume of water right here weighs much more than the iron does itself. And so that's why the buoyant force, which is the force trying to keep it afloat, is greater than the actual weight of the iron itself. Okay, and that's why ships are designed the way they are. So on the right side of the screen, you see two types of ships, right? On the left is more akin to a container ship, right? A much larger ship that carries much more weight, right? So its inherent weight may be greater. So the ship designers need to come up with a way to displace even more water, right? To compensate for that increased weight from all of those containers, all right? And so they do that by designing the hull kind of like this, right? As opposed to on the right where it dips down to a point, right? It's more square, so it carves out a greater volume of water. It still remains stable because let's do it that. It still remains stable because the hydrostatic pressures right here on all sides, perpendicular at all points, cancel out. Okay, same thing with the bottom. So the component on this side will cancel out the component on this side, and so there, in theory, shouldn't be a net force left or right. There's just a net force up, if you will, okay, from the water. On the right side, that's a less massive ship, like an aircraft carrier or a typical canoe, or like, a schooner, if you will, right? So that, its hull is designed like you see here. And so the hydrostatic pressures are small towards the top, bigger as you go down, and the largest at the very bottom. largest at the very bottom, pushing up, right? And so these are such that, again, the components on either side cancel out, right? Leaving only a vertical force upwards, okay? And so the weight of these types of ships with their cargoes are less than the giant container ships over here, and so their hulls don't have to quite carve out as much of the water like so, and so they can get by with a smaller, more pointed hull design. Okay? But it's all about displacing a volume of fluid that weighs more than the ship itself. I should say the ship plus the contents itself. Okay? And that's how objects float.